Yeah, we saw a little bit. So Milan was previously the PI of the project I'm going to present, and when he left for XMR, I inherited the project, and so here are the other members of the team, and that have more different kind of contribution. And so let me restart a bit from the beginning and describe the problem. So the motivation is really the problem of the raise effect, sometimes also called the beaming. And so here we really look at a very simple linear advection problem in a steady state. And we can see under the simulation the kind of numerical artifacts that we observe. And so I'm not an expert in this, but the problem in application is this kind of raise effect are completely destroying simulation. And in practice, this kind of deterministic, in particular in transport application, completely showstopper. And usually they rely on stochastic, like Monte Carlo methods for in the transport because of this raise effect. So really, the problem we were tackling is this raise effect and trying to get rid of them. So the strategy that was mainly Milan's idea. So like, and that he worked also with Stereo and some others, I think. And so the idea is that he named the general SN methodology. And so it's not an SN method, but the name means that it's kind of generalizing this. And so it takes a lot of inspiration from these methods. And so the general idea is that we're going to curve the coordinate system in the moment coordinate in order to mitigate those raise effects. And because of SN methods, there is a good reason to think that this is a good way to go. And so the way we're going to approach this problem is we're going to define those very complex coordinate system, and we're then going to have a more standard approach where we do multidimensional DG discretization of the advection operator. And so the only like maybe special aspect about this is, of course, it's a phase-space problem. So it's up to 6D dimension or even 7D if we had time. So like I will explain a little bit how we get there. But first, let me maybe describe a little bit what we look at. So here on those plots, we have on the left, we have a coordinate system where if we think about this, about a coordinate system where the origin or the axis of the coordinate always points in the same direction, we have here on the opposite, like a coordinate system where it's constant at each point of space, the coordinate axes are changing. So really, we're curving the coordinate system in this case. So here we're curving it in a polar way, for instance, and in the middle one, it's more of we follow some kind of a field, for instance, with the coordinate system follow the field itself. And here it's a bit of a schematic of what we could do in a whole room where we would curve the coordinate system a little bit following the characteristics of the solution in the idea. And so all this with the idea to mitigate raise effect. All this, as I said, is based on a general change of coordinates. So we're gonna differentiate. We have both the spatial coordinate and the momentum coordinate. So and we're gonna choose these very independently in some way. So in space, you can choose whatever is best for your problem. You can take Cartesian coordinate. You can take axisymmetric RZ coordinate. You can take polar coordinate. Why not? And in momentum, we always take polar coordinate inspired by a SN method. The only thing is we're gonna, in each point of space, we're gonna rotate this coordinate system as a polar coordinate system in momentum in order to try to optimize the raise effect. And so it's a bit what we see here when if omega is the direction of propagation of particle, for instance, of the so we have like the vector expressed here in a spherical coordinate, and we have this rotation matrix in 6D where which rotates this axis in each point of space. And so like the vector zeta is like the origin of the polar system, and omega 0 is like the rotation over the axis for the origin. But it's really like the origin of the axis. And so I will refer like depending on how we choose this transformation for the coordinate system. If zeta is an analytical function, then we call this analytical GSM. And if we use a numerical flux to determine this data, then we call this flux GSM, and I'll describe this much more later in this presentation. So like I wrote this, so like the main idea of the derivation of the rotation matrix is based on a Jacobian. So as usual, so if we look at we have two coordinate system, and so we have like the transformation that is expressed by this Jacobian minus transpose of the, so we have the new coordinate system expressed equal to Jacobian minus transpose of the old coordinate system. And so like the assumption that we do is that the new physical coordinates are not depending on the old momentum coordinates. So we don't curve according to the old moment coordinate. And this has another advantage is when we compute the inverse of the Jacobian, now we can compute the inverse analytically. So Q is a spatial coordinate and P is a momentum coordinate here. And so we have this analytical expression. We reinject this into the advection term, and now we have our modified scheme where with that takes into account this change of coordinate. And so in particular, something interesting there is we're gonna get advection in momentum when we do this change of coordinate, which we typically don't have unless we have forces, but we don't have forces. So it's gonna create a more complex advection. So now I'm going to describe a little bit more like the discretization approach. So starting with the mesh, how we build like the high dimension mesh in this project. So like the most basic building block, not so basic, is wrapping the MFEM mesh to have like curved 1D, 2D, 3D meshes. Currently, we don't support like AMR, but we're planning on supporting it fairly soon. We also like have a second data structure, which is just a Cartesian mesh, like analytical mesh. And so the purpose of this is first we can very easily build any arbitrary dimension Cartesian mesh. That's trivial, and they are very like they're basically free in terms of memory occupancy. Everything is very computationally efficient about them, and so. They're quite useful, in particular for the momentum, like when we discretize the sphere, something like that. And then the real data mesh that enables us to go arbitrary dimension is that we do Cartesian product or tensor product of meshes, and it's a bit like extruding meshes. And so like this, you can build a high of a dimension as you want. And so like the code itself like support like arbitrary dimension, everything we haven't gone beyond 6D, but like technically you can. And yeah, and so like the nice thing about this Cartesian product is that it's a lazy data structure, so it doesn't compute anything when you build it. It just computes the cells of the mesh when you request them on the fly. And so like this, you can have very low memory footprint, and it's not having like the computational cost is also not very high. And so in order to like reconciliate like those different mesh data structure, like we use a new mesh interface that is built on top. And like what was important is that this mesh interface is actually extremely simple. We only have two functions. It's get cell and get face neighbor info. And that's all you need to support like any data structure. Like if you want to add I don't know, you have an idea on how to build a different type of mesh that's useful for you, it's going to be very optimized. You just implement those two methods and it works out of the box, like nothing have to change otherwise in the code, and you can run it. And so so that's, let's say like for instance, you even like you want to use your own mesh data structure coming from your library. You could use it, implement those two methods, and then even run your mesh into MFEM, use all the MFEM infrastructure like that. So that's quite neat in my opinion. So and then the cells themselves also need to have those three methods in order to have a full grammar for the finite element method. So here I really try to map the mathematics to the methods one-to-one, so that we see like here as a method, and next there is the mathematics that is trying to represent, and keeping it as small as possible. So just giving a quick example, here is a trivial one. So we take a 2D mesh and a 1D mesh, and we get this kind of a 3D extruded mesh. So that's fairly simple. So as I said earlier, the memory footprint of this is going to be 2D plus 1D, not the product of the two. And so it's going to get especially interesting if we go to 6D. And yeah, so in practice, what we do is we have one mesh for space, one mesh for angle. So here it's represented as a sphere, but really what we do is a Cartesian meshes, where a mesh with angle on the sphere. Instead of having like mapping the sphere itself, we map it's just a Cartesian mesh for the angle, for the direction of propagation of the particle, and then we have a 1D mesh for the energy outside the particles themselves. And so that's how we go 6D, right? And so then after that, like as I said earlier, the DG approach is very standard. We do a advection scheme, DG scheme, right? Not upwind, nothing very special about it. And so as you see, like you kind of see that all the methods that we saw earlier, like the mathematics they were representing, is all you need to write this weak form, and it gives you like the feel of why this is the only thing you need and you don't need anything else. And so one of the nice things also that we do is we use matrix free, and it's critical to go to high dimension. And if we look at the memory occupation and the flops when we compare to a sparse matrix, so when we look at the memory utilization of a sparse matrix, we have np plus 1 to the 2d, where n is the number of elements, p plus 1 is p is a polynomial order of the basis function, and d is the dimension of the problem. And so one important thing is we see that the sparse matrix has a arithmetic intensity of 1, meaning that no matter what you do, it's going to be memory bound, like the quality of the computation. So if you want to run faster than a sparse matrix, you have to move less data. It's not about the flops, it's really about data movement and nothing else. And so like this is what matrix-free approach, this is what matrix-free are so good. And so when you do matrix-free, you lower this memory utilization from to n to the p plus 1 to the d. And if you don't do some factorization, we saw like you keep a flop count that's pretty high, that is the same as a sparse matrix actually. I mean asymptotically. And one of the problems, if you don't use some factorization, you also get a p to the d arithmetic intensity. So for either high dimension or high polynomial order, you're gonna go from a memory bound regime to a computation bound regime, which is something we typically don't want. It will impact a lot your performance, and you could like run slower than a sparse matrix or all this kind of thing. Like you're gonna run much slower than you want if you do that. And so if you use some factorization, on the other hand, you go to the p plus 1 to the, to the p plus 1. And so that means that you can have p plus 1 to the d speed up, which is a good result. So this has been, like Tanyo has showed this, how you can do great things for high order, but you can do even greater things for high dimension with this, of course, because the factor is there, right? And so well, I'm going to go very quickly because we saw that a lot. It's like how you derive this matrix free, and about this is all the seed work. Like, so here it's for a discontinuous Galerkin approach, so it's a slightly different. For the volume term, it's actually simpler. So, but the 3 steps are always the same. You express the integral in reference coordinates, the weak form. Then you use a quadrature rule to approximate your integral, and then you transform the sum that you have here in a sequence of operation. And so basically you get for DG, you get a G transpose D B, and where B and G, so G has a different semantics than when other people write it. Here is to say the gradient, and B is to say like the interpolation of the values of the field. And so why we get memory saving is because the only thing that we really need to store, if we want to store it, is this D, right? And the degrees of freedom themselves, of course. And so if you store this D, this is what is known as partial assembly. And here, because we do 6D, we don't even want to store this, so we're gonna even compute this on the fly. So we compute absolutely everything on the fly. The only thing that we store is our degrees of freedom themselves and the mesh. And if the mesh is analytical, then we don't store anything besides the degrees of freedom, right? And so this is what the operator looks like. Then you do something very similar for the phase terms. except like you need to do to access your neighbor degrees of freedom. And so like there is this P operator here, which is basically you need to do some kind of permutation when you compute your numerical fluxes for the DG method. And this is a little bit tricky, especially when you start doing phase orientation in arbitrary dimension. It can get a little bit complicated, but it's doable, of course. And so that's all you have to do, right? So here it's a per element approach. You can in MFEM it's currently implemented as a per phase approach. There's pros and cons to each. The reason why we went for an element approach is because we were targeting a sweep algorithm for solving the problem, and so having a per element approach is more suited for a sweep algorithm. So here a quick reminder on what is the sum factorization trick. It's just a reorganization of the sum terms. So you just reorganize this and you go from algorithmic complexity up to P to 2D to P to the D plus 1. Okay. So now looking more like a roofline model, diving into the performance of this. So here I just look at the data movement of the operator. I don't care about the flops at all. The idea is the best performance we can achieve is say that this operator is going to run as fast as a mem copy, and there's no way we're going to run faster than a mem copy, right? So the theoretical max performance is a mem copy here. And so we compare like the sparse matrix with a partial assembly and different flavor of fully matrix free according to what type of mesh we have. If the mesh is purely analytical, if we have a linear space mesh, and then the momentum is analytical or quadratic space mesh. And so what we see here is like in 3D, like the sparse matrix bytes per DOF remains somewhat in control, but we see that it grows quickly as we increase the polynomial order, and in 6D it really gets quickly out of control in terms of bytes per DOF. And so that's where like a matrix-free approach shine. And so in particular, if we compare like partial assembly and matrix-free, we see that an interesting aspect is if you do fully matrix-free on an analytical mesh, like the number of bytes per DOF is constant no matter what the polynomial order and whatever the dimension of the problem. So you're not moving more data if you have higher polynomial order or higher dimension. You get more computation, so you might get computation bound, you might get other issues, but as such. And also, if we also see that if we take unstructured mesh just in space, which is a common scenario, we don't really use any more data movement. Like it doesn't significantly impact the amount of data movement in 6D because the mesh itself is 3D and the DOF are 6D, so you get much more DOF for your solution than for your mesh itself. Okay. So now looking at the performance of a mass operator, starting simple. So here is just CPU result. It's a machine Quartz. Actually, I think it's been retired since this benchmark. And so in dotted line, we get a theoretical max. So really, it's impossible to go faster than this on this architecture. It's based on the bandwidth that's here. It's using OpenMP, this benchmark. And so we see like in green, this is a matrix-free absolute maximum. In purple, this is partial assembly, and in red, you get the sparse matrix. So we see that in 3D on CPU, we're fairly close to the peak performance for a mass operator. In 6D, we definitely see, so okay, let me see, I should describe a bit more what we're looking at. So what we're looking at is the throughput, right? So the higher, the better in terms of DOF per second, and X, we have the polynomial order. And so those plane line are how many quadrature points we have, right? So the more quadrature points, the more computation we have, right? But not more data movement because we do everything matrix free. So like we don't move more data, we have more quadrature points. So Q equal P is not something we would use in practice. I just put it here to see like the impact of increasing the quadrature. And what we see is that as we increase the quadrature, we have a fairly big impact on the performance, which means we're actually not memory bound, probably. We're probably, the cause of this is that we are computation bound, and as we increase the computation, result in a longer computation time. Okay, so now looking at, I did two advection operator, so in a 3D and 6D. So here again we see like slightly lower performance. Oh, sorry, I also forgot to mention like we have two different dotted line. So there is a theoretical max throughput, and there is a like the small dotted line is a measured max throughput. So literally, I do a mem copy and I look how fast I can do that, and on the given architecture, and this is my point of comparison. And so like in 3D, we see that we achieve very close to this peak performance, but we see in 6D that the advection operator has quite a big impact as we increase the quadrature rule, and we see that the limitation of the CPU. This summer, we had a summer student, Amit Rotem, that did excellent work at porting all this to GPU. I mean, all this, no, actually, he did only the math, and the advection operator is remaining. But nonetheless, we get extremely encouraging results, as you can see here. So, like, the color change a bit the semantic. In green is GPU, in blue it's CPU. So interesting result is that in 3D we actually have the same performance on CPU and GPU. That's when we use OpenMP, of course. If you use a single thread, you're not going to see that. And so we see that the GPU is actually fairly heavily underperforming. And that, yeah, like the GPU, I guess it's still not like great, but when you go to 6D now, like you see that something that's completely different. We see, like as previously, that the performance on CPU decreases as we increase the dimension of the problem, but on GPU we are not computation bound. So now we can use more of the bandwidth because we have very regular memory accesses, even more so in 6D than in 3D. So now we see that we are getting for order 2 and 3 very close to peak bandwidth actually. Like I put 900 gigabyte per second for a V100, that's vendor numbers. If you're never gonna get that in practice, so you get actually very close to peak performance here. So that's excellent news. Like we really want to know like how good we get for advection, but and in terms of gigadov, like we are at like 31 gigadov here per second, so that's much higher than what we observe in 3D. So we run actually quite a lot faster in 6D than 3D, which is a fairly unexpected result. Of course, you get more degrees of freedom in 6D. So like we didn't solve that. We solved the computational cost, but we don't solve the memory cost of the DOFs that are in 6D, right? So now I want to switch to some benchmark problem. And so the first one is a very simple one. So we have this box with a hole in the middle, vaguely inspired, hole run inspired. And so on the outside, we do a very simple homogeneous inflow condition with a value of 2. In the inside, we do a purely outflow condition. And in terms of momentum, so we're going to compare like a kind of a standard coordinates, a polar coordinate system where we don't change at each point of space the orientation of the polar coordinate, and with a cylindrical GSM where we're gonna have the origin of the polar system always pointing at the center of the mesh, right? And that's because like the solution that we expect for this is spherically cylindrically symmetric, right? So that's the intuition there. And so first I want to show you what happens if you don't do the change of coordinate, and showing you that like the polynomial order doesn't fix anything. So if you do like here you have 0 order, first order, and second order DG, and you can see like very strong raise effect. And what I'm plotting here is scalar flux. So we take our density of particles and we integrate over the angle to have those 2D plots, right? And so this is nice plots, this looks beautiful, but this is not what we want at all. So now if we compare like this standard GSM with a cylindrical GSM, and so this n omega is a resolution that we use for the angles, like how much resolution we use for describing the direction of the particles. And we see that even at extremely low resolution, as 4 finite elements to describe the sphere, we get perfectly is a stronger, but we get very good spherically symmetric solution. And as we increase, the solution gets better. We see that at 4 we get slightly unstable in the corners, but nonetheless it's far better than what we observe when we use a standard coordinate system. Okay, now moving to a slightly more, well, actually a lot more complicated problem where we take an inflow condition, which is x squared plus y squared to the fourth. So technically you get like inflow at the corners of the mesh. And we're gonna look also at standard versus cylindrical GSN. And so now like the result is a bit more complex. So here I plotted in log scale, so it makes everything look a lot worse than it actually is. But we can observe, especially at low resolution, where we had very clean solution, we can still see some red effect with very different kind of nature. Like they don't look the same as what we observe with the. But as soon as you increase a little bit, we see that the rays effect disappear fairly quickly. So here, that's for second order. And I also show you here what happens when we look for different polynomial order. And so nice thing that we have with this GSN method is when we use cylindrical GSN, we see that as we increase the polynomial order, it dumps the rays effects much faster than if we use a standard GSN. And so like the polynomial order seems to perform a lot better with the appropriate coordinate system. Is an interesting property. Now showing you quickly RZ cylindrical, RZ axisymmetric test case. So this problem now is a 4D problem. So we have 2 dimensions in space, but really a 3D problem, and a 2D in angle because it's a 3D problem. And we're going to compare like cylindrical versus spherical GSN. So cylindrical, we have the polar axis always pointing, the polar origin always pointing at the axis. And whereas if we do spherical GSN, the origin of the polar is going to point at the origin of the mesh, which is down here, right? So if we compare here again, like we have some similar result as previously, we see that cylindrical GSN doesn't do the trick. We observe like some fairly strong rays effect, but with a spherical GSN, we observe a perfectly symmetric solution. And the solution are slightly different with order, but not too different. Yeah, in the interest of time, maybe I'm going to skip this. And now, yeah, as I mentioned earlier, the flux GSN. So the idea is really what we see is that if we align the coordinate system with the solution in some way, we eliminate and mitigate the ray effects. So the idea here that really comes from Milan is that we're going to use the first moment, also called the net flux, which is this integral where we multiply the density by the p, and we're going to use that to determine our coordinate system. So now we get into a nonlinear problem, right? Because the coordinate system is determined by the solution of the problem itself. So the algorithm goes as follows. We first compute an analytical solution using analytical GSN, where we give ourselves the coordinate system, and then we compute the net flux. Well, it's going to be an L2, so we still first project it into H1, otherwise we're going to get a lot of problem, but that's doable. And then we do a fixed point iteration for now. So we compute the solution using the flux of the previous time step as the coordinate system for the next solve of the problem. And so now this is a little bit what the spoiler Milan showed you. And so a slightly different problem. Here we put 4 minus x as an inflow to get a non-symmetric solution. And so this is what you saw a little bit earlier. So we start with an initial solution with a lot of rays effect, and we see that at each nonlinear iteration, we have a damping of the ray effect, and it converges to 8 relative error to 1 minus 6 in 19 iteration, with a perfectly smooth solution at the end. Okay, so that's it for my talk. So like, yeah, the main thing is like, I presented like the analytical GSN and flux GSN methodologies, and we showed that they can efficiently mitigate rays effect at low computational cost. There is also some caveat I didn't go into detail in interest of time, and yeah, we also saw that matrix 3 can mitigate efficiently the computational cost of high-dimensional simulation, and on GPU in particular, the higher the dimension, the higher the throughput. Okay, I think I'm going to stop here and take questions. Do you have any?